Hello, my name is Amanda Baker,
I'm Pavan Naidu.
and we're going to walk you through our analysis of and work in identifying toxicity and bias in online comments. The big question we want to answer is how do we keep online discussions inclusive and safe for everyone? We're all familiar with online platforms like Facebook, Reddit, Instagram, where comments like the one on the screen are very commonplace. These types of comments can create unsafe environments for many groups and very often discourage or crush open discussion online. There are many algorithms already in existence that work to flag toxic comments. Unfortunately, even for companies who have implemented these algorithms, like the New York Times, there's still a ton of manual labor involved in reviewing the flagged comments. In fact, the New York Times employs a team of 14 moderators who manually review almost 11,000 comments every day. The need for moderators is due in part because toxicity identification algorithms tend to introduce bias when learning to catch toxic comments. Many words that are benign by themselves quickly become associated with toxicity. For example, the word women was the seventh most common word in a random sample of 50,000 toxic comments. What this means is that many of the populations that these algorithms are trying to protect, populations like specific genders, races, or sexual orientations, are actually penalized further by these models. So the big question is, how do we identify toxicity without bias? How do we make sure that one comment with the word woman in it is clearly marked as toxic, while another comment with the words weep and girls is not? The dataset we use to train and test our own toxicity identification model is the Jigsaw Unintended Bias in Toxicity Classification dataset. Jigsaw, through the Conversation AI team, is dedicated to building technology that protects voices in conversation. And to facilitate that goal, they provided a dataset of almost 2 million online comments that have been human annotated with a toxicity score, identity labels, and additional notes like the identity attack score, insult score, and more. When we explored the dataset, we saw that it was very heavily weighted towards non-toxic comments. Comments with a score of zero point 0.3 or lower are generally considered non-toxic, so we used zero point 0.3 as our toxicity threshold. We also looked at a correlation matrix of all features, and out of everything, including insult and threat scores, the most strongly correlated feature against the toxicity target was identity attack. So it's very clear that identity labels will play a role in toxicity identification for most algorithms. Interestingly, when we took a look at a scatter plot of toxicity against identity attack scores, we see that while a high identity attack score is very closely related to a high toxicity score, a high toxicity score is not necessarily because of a high identity attack score, which further complicates the bias reduction process. Before we started building our model, we first prepared the dataset by storing the top 10,000 words, creating a binary target variable to identify if a comment was above or below the zero point 0.3 toxicity score threshold, undersampling the data to balance the set, tokenizing words, removing stop words, and stemming words. This gave us a training set of about 207,000 records in each class. Next, we looked at 200 most common nouns appearing in toxic comments. Some examples from one random sample of 50,000 comments are on the screen. The results were a surprise. Based on literature from Jigsaw, we expected to see many more triggering identity words. Instead, the results were generic, largely political, or even self-referential. See the word comments at number 20. However, one common theme across every random sampling was that gender was very common in toxic comments, which we took note of to use in some of our later models. How did this go? Pavan will explain.
Thanks, Amanda. I will now walk us through the model building part of the project. From our exploratory analysis, we decided on a plan to approach this problem using recurrent neural networks or RNNs. The reason for picking RNNs is that humans don't start thinking from scratch every second. As we read a text, we understand each word based on our understanding of previous words. Our thoughts are persistent, and RNNs address this very issue of information to persist. Our RNN sequential model has 5 layers in total. The image on the left shows the model summary, and the image on the right shows a graph of the model taken from TensorBoard. Starting with the embedding layer, which takes a padded input sequence of length 100, and each word is represented in 300 dimensional space. Then we flatten the word sequence for the dense layer of size 64 neurons with ReLU activation. Further, we added a dropout layer to avoid overfitting during the model training phase, since the validation error started to increase after few epochs. To get a probabilistic output, we used a dense layer of one neuron with sigmoid activation, and the model was trained with RMS prop optimizer with binary cross entropy as loss function. We then broke our approach into two versions of word embeddings, custom and GenSim word embeddings. And from there, we used each of these models by considering variations of identity words as stop words to nullify their effect of false associations. Each of these approaches can be categorized into four categories. All words model where no stop words are removed, which is our baseline. LGBT words as stop words because Jigsaw specifically called out for these words and their false associations. Gender-based words on what we observe from toxic comments in our data analysis. Custom list of identity words based on thought leaders in toxic comment discussion. We got a pretty good baseline model which is built with custom word embeddings, considering the area under the curve for ROC and PR curve. But not all false positives are equal. Some false positives have inappropriately high toxic score, which can be attributed to unintended biases learned by the model. Therefore, we focused on reducing the number of false positives by improving the recall score. Training our own word vectors may be the best approach for a given NLP problem, but it can take a long term to learn, and perhaps some expertise in finessing the input data and the training algorithm is required. So we thought of using pre-built word-to-vec embeddings from Google, which are trained on Google News data into a GenSim model. It can be used to understand word similarities. Say if we try to find words similar to gay, we get homosexual, lesbians, transgender, and likewise. Although pre-built word embeddings provide us the advantage of faster model training, it didn't perform particularly well when we tried out our different approaches. None of these performed well relative to a baseline model in terms of improving the recall score or other metrics. So we continued with custom word embeddings. We use a custom embedding layer which learns the word similarities based on the word occurrences and the word sequence. For this, we need to specify the dimensionality of a word vector, then the network learns during training phase. The models were trained with 300 dimensional word vector representation. Further, we use tsne to represent the words on a 2D scatter plot. And if we observe closely, it appears that the gay, abuse, liar, accept form latent close associations, which is interesting. Using custom word embeddings, we saw an improvement in the recall score with different custom stop word lists, while retaining the EOC around 90%. And the model with gender as stop word list performed the best in terms of recall score of 92%, which is unsurprising because gender related words appear in most of toxic comments during our data analysis. Let us draw your attention to the confusion matrix, specifically the false positive. We see a reduction in the false positives from our baseline model, which was 4,968 comments, and we see this as an improvement of reducing the biased associations. We saw how computers can learn to understand the nuances and the context of abusive language. If successful, machine learning could help publishers and moderators improve comments on their platform and enhance the exchange of ideas on the internet. It is quintessential to ensure that toxicity identification model protects the group they mean to protect, and we learned that using data to determine words which shouldn't be associated with toxic comments improve the recall score. In the future, we plan to try out multi-classification models to help us identify more subtle forms of toxicity which are critical for social media platforms. In sum, we believe investing in models that can understand the structure of false positive comments will be beneficial in removing the unintended bias. For those of you who are curious, we use packages like TensorFlow, Keras, and Scikit-learn, and feel free to reach out to us regarding any further discussion. Thank you for watching.